There we go. Alright, so now I'll turn up the volume a little bit. You guys hear that?
Yeah. Is that like a really super
Not
high
real loud.
frequency?
Let me see if we can make it a little louder. Sometimes these things have a little bit.
So the louder it goes, the bigger the volume gets?
Not necessarily.
Is there a way that we can look at a computer and play music? Well,
We're going to go there.
It's really
I'm going there.
So now, I can tweak the frequency. Tweak the frequency. At certain key frequencies, when the wavelength ends up being like integer multiples of the tube length, you might see a standing wave pattern in that. I'm just going to try and see if we can find the best way to do it. John, you've done this a bunch. Are there particular frequencies that work well?
Yeah. I think it was, we got it at lower.
Yeah, lower.
It was like, more like a. There you go. Right there.
There you go. Okay.
Oh.
All right. You see that?
Beautiful.
Yeah, we're going to go a little higher. Alright, so what's happening is at this point there's relatively constant pressure, and at these low points the pressure is really oscillating up and down high. Then you have constant pressure here again, a lot of oscillation, constant pressure here again. Those constant pressure areas are called nodes, and the big vibrating areas are called antinodes. Alright, and this is the way it actually essentially see variation of pressure inside the tube. And if I increase, let's see, what am I at now? I'm about a little over 400 hertz or so. If I go up to about 800, theoretically, should be able to see it again, but like twice, half the wavelength. There we go. Okay.
There you go.
So that's twice the frequency, which means the wavelength is half as much. So the spacing between these little peaks should be half of what it was before. We're going down. We did like just a half of it. So now we've got a case where got the speaker producing large amplitude vibrations here. You've got a node about in here somewhere. Is that about where it's tallest? Turn this one this way. Yeah. So big vibrations there, no vibrations here, big vibrations here, no vibrations here, big vibrations where it bounces off the other end. You can actually measure that. We have a meter stick around. Let's go ahead. Pick it up, maybe. Go back up.
So the higher the frequency, or the higher the pitch, the more waves you're going to see?
Yes. Thank you.
Can you make it so high that they're all just
Yeah, make the tsunami wave.
that's about 47 centimeters. Alright, and that's like turns out to be half a wavelength. Because you've got to do the full sine wave, toss that through and back up. Alright, so that's twice that is going to be what, 94 centimeters. So you guys know that sound travels through air at about 340 meters per second. Right? It doesn't go exactly the same speed through natural gas, but it's close to that. So can you guys calculate what frequency this should be? You've got a wavelength of, let's ballpark it, wavelength of a meter. Alright. Goes 340 meters per second. Let's say 333 meters per second, for example. 333 and a third meters per second. What's the frequency? Should I turn it down so you can actually think? You got an answer yet? Use some Jeopardy music. Need some motivators. So 333 meters per second, let's say, for simplicity. Right.
And a wavelength.
It's a meter. Wavelength is a meter.
Wouldn't it be the same as the?
What's the frequency?
Would it be 300?
Yeah. Are you working on it? Okay.
What's the space out?
We're going to say 333.
That number.
333. That number then.
So what's the frequency? How many
One
hertz?
over that?
What?
333 hertz.
333.
Yeah, 33 hertz.
Yeah.
Going to meter? Yeah. Alright, so pointing to this thing here. Pointing to this thing here, it's not that. This thing, now this is not particularly accurate, but it's showing something more like 400 hertz, but probably close enough to ballpark. Now, the variation is likely to be due to the fact that the sound is going to travel differently through the natural gas and just air. So different densities, so on. So that's probably where the offset comes. That basic idea works. Alright, so now we'll go to something a little more random.
You do so low that we can't hear it.
You won't be able to see much. That should take you through that. Alright. The original graphic equalizer.
We'll have this at like a patio dinner party.
Yeah.
That's so cool. Just surrounding and blow it up. All right.